Okay, so hello there everyone. We're going to continue with our module 0 and number theory, and we're now here in direct proofs. So in this video, we will explain a simple way to prove theorems or propositions that have the form of conditional statements. So remember, a conditional statement is in the form of P implies Q, or if P, then Q. So the technique that we're going to present here is pretty much written in the title. So that's what we call a direct proof. So to simplify this explanation, this video, our first examples will involve proving statements that are almost obviously true. Okay, thus we will call the statements proposition rather than theorems. Remember that a proposition is a statement that, although true, this is not significant as a theorem. So to understand how the technique of direct proof works, suppose we have some propositions of the following form. Again, we will use this. P implies Q. Okay, and I'm going to give you one example of this. Outline our outline for a proof, which is a direct proof, would be something like this. So it's a common practice to write the word proof, okay, on it. But before that, of course, we need to write the proposition or whatever it is, if it is a theorem. So we need to write it here, proposition. Okay, so whatever that is, commonly it's bolded and it's seldom it's underlined, but here, since I cannot bold it, I will put it underlined. So we can put if this proposition P, then this proposition Q, the conclusion will happen. So the outline would be something like, we'll write a word proof. Usually it's italicized or bolded, then put a period on it. So what we're going to do is, suppose P is true, we're going to have this arguments here. Sorry, suppose P is true. So we're going to put the arguments, the proper arguments, wherein we need to make sure that the arguments are logical, it is in a clear way, and it should be concise and brief as much as possible. We can therefore say at the end of the proof statement that we will be saying that directly, that therefore Q happens. Okay, and we usually end it with a box like this, okay, to indicate that the proof is done. So this is, in some books they use QED. This box actually means QED. That's called erat demonstratione, meaning the the work is demonstrated or the proof is done, something like that. All right, so that's Latin. Let's give one example of a proof that is taken from the definitions that we have had on our previous video about odd and even numbers. So let's have this as our example then. So let's go down here. So I have a proposition. I'll just call it a proposition because it's not that strong to be called a theorem. So proposition. Okay. So the proposition is quite simple. If we have a number x, if x is odd, then if we're going to square that x is also odd. So this is pretty much a very simple example of a statement. That's why it's called a proposition. Um, I'll just have for all x, which is equal to 2a plus 1, which is in the form of an odd number, uh, for all a in the integers. Okay. So let's have this now. What we are going to do with this proof, how do we prove this? Is that it will be something like this. We're going to write first the word proof. Again, usually the word proof is italicized or bolded. I'll just make it underlined here and with a period. We're going to first, our outline would be, we're going to suppose that x, let this be our P, of course. This is our P statement. And this will be our Q statement. Okay, so these are just quantifiers. So this is the statement of the Q. So if our hypothesis is true, therefore the conclusion is also true, since that's the proposition or the conditional statement says. So what we're going to do is, suppose P, that is, suppose x is odd, we should end up in some sort of way wherein we're going to end the proof, wherein we're going to say that therefore x squared is also odd. And then of course we need to end it with a box at the end, which is QED. Okay, so supposedly this will be the form of our proposition. It will be our duty to form in the logical arguments in such a way that we will end up with x squared being odd from the given that x is odd. All right, so let's start with this. I'm going to delete this. Maybe it will need more space or less space. So first, we're going to make use of definitions of axioms that we have learned from this. So since we suppose that x is odd, so therefore we can see since x is odd, so therefore it should be in a form of 2a plus 1, right? So then we can say that then x is in the form of 2a plus 1 for all a um, in the integers. All right. So this is where did we get this? It's better if you're going to write the reason why you got this statement here. So in some articles in mathematics, you can see by definition 1, by axiom 2.3, by theorem 3.7 or whatever. Where we got this is by the definition, by definition, or by that definition, sorry, of an odd number. Okay, so we're getting there one step at a time. Thus, if we have x is equal to 2a plus 1, we want to show that x squared is also odd. So what we want to do is to square this. So thus, what we have is x squared is equal to quantity 2a plus 1 squared. So by squaring a binomial, that's a pretty common standard operation. So in mathematics, so we have 4a squared plus 2a, rather 4a plus 1. Okay, so what we can do with this is that we want to do or restructure the 4a squared plus 4a plus 1 into something like in this form. Because what we want to prove is that x squared is an odd number. So it should be something in this form. So what we want to do is we want to have an a. Okay, imagine a to be anything because a could be in any a could be any integer, but we want to have this form of 2 something plus 1. Okay, 2 something plus 1. So what we can do here is that the force, we can get that force out, and then we just need to get the 2. So get the 2 out. What will happen is that we have a 2a squared plus 2a close quantity plus 1. It fits. Okay, plus 1. Okay, so what we can see here is that x squared, hence, that is, we can further clarify that is x squared is equal to, we'll just get the two final two final portions of this long equation here, that x squared is equal to 2 times the quantity of 2a squared plus 2a close quantity plus 1. So we can denote and we can let this form here, this 2a squared plus 2a, into some variable. Okay, wherein 2a squared plus 2a is going to be equal to that variable. So what we will do is we will let some variable, say let's make it b to make it simple. Let b be equal to 2a squared plus 2a. Hence, we have x squared is equal to 2b plus 1, where b is equal to 2a squared plus 2a for all a in the integers. Okay, now since a is in the integer, so therefore this, whatever the value is of b is, it's going to be an integer, and whatever the value of b is, it's going to be an integer for sure. And we put this integer here in this form here. So that integer times 2, which will make it even, whatever the integer is, and then we're going to add 1. Therefore, this form is going to be an odd number for sure, hence telling us that x squared, if x is odd, squaring an odd number will definitely give us also an odd number. So therefore, with this, we can say that x squared is odd. All right? So x squared is odd. So this is by definition. How did we do that? By definition of an odd number. Okay, and then that's the end of our proof. So we want to put a box, a square box here, or rather, yeah, a square box. It's not really squarey in this form, right? Seldom in some books they put it at the last part here, but I want to put it here. It's okay. Depends on the book that you're using. So this is the first example of a direct proof that we're going to show. I think it's pretty clear. What we started with a P, the hypothesis, and we ended with the conclusion in which we wrote our arguments pretty much straightforward, thus calling it a direct proof. Okay, so that's it for this video. Thank you very much for watching. I hope you would like and also subscribe, and see you for the future videos. Okay, thank you.